Another way to connect capacitors is what we call in parallel. Parallel connections means you have a wire that comes out of the battery, but then it branches. It branches and goes to two separate capacitors. So one branch goes to one capacitor, the other branch goes to the other capacitor, and in turn they come back together and come back to the end of the battery. Yes?
Will we ever have a problem where I'll be in parallel and series at the same time?
Yes.
Oh boy.
You will have a combination. But it's not too bad.
It doesn't seems a little daunting.
It is daunting at first, but with a little practice, it's not too bad. So, again, in equilibrium, charges have moved until the positive end of the battery and everything it's conductively connected to reaches the same potential. Since the battery is conductively connected to the left side of both capacitors, the left side of both capacitors ends up with the same potential as the left end of the battery here. Likewise, the right side all ends up at the same potential as well. So what can you tell me about delta V1 being the voltage drop across the top capacitor versus delta V2, the voltage drop across the second capacitor, versus the battery?
I assume they have to add up to delta V total.
But look at the picture. What did we say about all the blue side?
It's equal.
It all has to have the same potential. What about all the right side?
It's all on the same potential.
So if there's blue to red, blue to red, blue to red, they all have to have the same potential. Delta V total is the same thing as delta V1, which is the same thing as delta V2. Again, this is conservation of energy. If you think about it, delta V total is what's going into the circuit. If you were to follow a path from the left end of the battery back to the right end of the battery, whatever the battery put into the system, the circuit elements would have to take out. So delta V total was put in. I can follow a path that goes through the middle capacitor and back to the end of the battery. If delta V total was put into the circuit, delta V total had to be taken out by C2. So delta V2 has to equal delta V total. Whatever's put in has to be taken out. That's conservation of energy. Or I could take the other path and go up through C1. C1 would have to take out all of the voltage. So I have a choice. I can go through C1 or I can go through C2. Either way, I have to have the same amount of voltage taken out of the circuit. So that's why delta V total is equal to delta V1 and is equal to delta V2.
Can you only go through one at a time?
Yeah.
Well, like,
I mean, it's like hiking. If you go on a hike and there's a break in the path, you can only take one trail or the other.
okay, so like when you set this up, they'll break the path to C1, forcing everything to go through C2.
If you were to break the path to C1,
Yeah.
then yeah, everything would have to go to C2.
Okay.
That is correct.
So when they use these, though, they do break the path. They don't just leave both open,
No, you can leave them both connected.
and everything will just go one way or the other.
Yeah. So there will be a total amount of charge that's forced to move. Some of it will come this way. Some of it will go that way. But any one given electron can only go one way.
It's like Christmas lights. You know, the older Christmas lights are done in series where if one goes out, they all go out. But with the newer ones, they go in where they're parallel, where if one will go out, the rest will stay on.
Yes. Exactly. Okay, so the voltage has to be the same. That's conservation of energy. If you follow the path, you can see whatever's put in has to come out. through whichever path you follow. The other equation we get, Q total, whatever charge this battery is forcing to move, when it reaches that junction there, when there's now a choice, some of it will go through the middle branch, some of it will continue up and go to the top branch. So Q total is not going to equal Q1. Q total is not going to equal Q2. Q total splits. Some of it goes up, some of it goes through the middle. So Q total is equal to Q1 plus Q2. That's a conservation of charge equation. It's saying whatever total amount of charge flows to that junction has to keep going. Now some of it will go one way and some of it will go the other way, but it has to keep moving in general. So if we wanted, like we did with the series circuit, if we wanted to treat this as one equivalent capacitor and to find its equivalent capacitance, it's not the same as the series. In series, we have the 1/over relationship, which, by the way, I forgot to point out. Did you notice when we did that example that the equivalent capacitance was smaller than the individual capacitors we had? We had the 5, the 10, the 20, but the equivalent was 2.86. That will always be the case when you connect capacitors in series. If you connect them in series, you always get an equivalent capacitance that is smaller than any of the individual capacitors. To figure out the equivalent capacitors in parallel, we're going to use this equation and the middle equation over there. Q total. Well, Q total is the same thing as C equivalent times delta V total. Q1 is the same thing as C1 times delta V1. Q2 is the same thing as C2 times delta V2. But in parallel, all these delta V's are the same. So the equivalent capacitance in parallel is simply the sum of the individual capacitors. Overall, you get a bigger capacitance by connecting them in parallel. So if we plug in some numbers, let's say we have a 10 microfarad capacitor and a 20 microfarad capacitor and our 10 volt battery. Well, the question I asked with the series, what is delta V across each capacitor, is actually really easy to answer. Each of these has to have 10 volts. That's easy enough. The charge, though, will be different. The amount of charge it has, if we solve our middle equation for Q, Q is C delta V, capacitance times voltage would be 100 microcoulombs here. This one would be 200 microcoulombs. The middle capacitor got more charge because it has a higher capacitance at the same delta V as the smaller capacitor. Turns out it wasn't necessary to break it down to an equivalent. It'd be easy to. The equivalent capacitance would simply be 30 microfarads. The total charge that is forced to move is simply 300 microcoulombs, because that's 10 volts. We could easily find the energy for each capacitor, because we know the capacitance and delta V for each capacitor. So we could easily find out the amount of energy each stored. We could easily find the total energy, because we know the equivalent capacitance and the total voltage. So yes, the trick is going to come when we have a combination of series and parallel in the same circuit. It's not really too hard to do, it just will take a few steps to get to the answers. Because you have to look at series first, and then parallel, and so forth. Do you recognize how to tell the difference between series and parallel? Parallel, there's going to be a branch, so that you have a choice. If you were to take your little field trip around the circuit, you have a choice where you can go through one capacitor or the other. That's what makes up parallel. Series, you have to pass through all of them.